Hello, I'm going to do an example here from the book. This is from 2.8. This one pertains to a beam, a hanging beam. So the idea is, here I'll draw a picture. So we have this beam that's supported at two ends, clamped, right? And then it's actually clamped in there. And then between those points, it's going to sway like this, and we're trying to find the shape of the curve in this situation. So here we go. Okay, so this is number 16. We know that we start with our equation as derived by the physicists or engineers in this area. That is that we have this differential equation here with the right here where EI and W are constants, right? The clamping or the fixed conditions are stated here that we want Y at position X equals 0 to be 0, and we want Y prime at 0 to be 0. That's the clamping position. And similarly, we would like that to happen at the other endpoint, L. So if we anti-differentiate this differential equation, we get the general solution as is indicated in the book. I wanted to point out there's an error in the book. Actually, in the book, this 4 is a 2, but clearly that's a 4. Okay, so then if we differentiate that, we see that we get the what's on the following line. And now we want to use our endpoint conditions to find these constants A, B, C, and D. Okay, so doing that, if you look at the first conditions at 0, y of 0 equals 0 and y prime of 0 equals 0 tells us that both D and C have to be 0, which leaves us with the solution of this form. Okay, now what we would like to do is use our other two conditions, that y of L equals 0 and y prime of L equals 0. So we plug in L and we get this equation here. Okay. And then simplifying that, or actually factoring it, we see that we get this expression right here that must be 0. Similarly, if we calculate the y prime and evaluate that at L, we notice that we get this expression right here after factoring. So what happens then is we get the system of equations. To see here, we get A times L plus B is these two equations, which I'm calling E1 and E2. Okay, so if you take, when you solve a system of equation, you have these operations you can perform. So if I take minus 2 times the first equation plus the second equation, we can arrive at this conclusion that A times L has to be equal to what's on the right-hand side of that equation, or in fact that A is given by this quantity. All right, now substituting that quantity back into equation 1, we see that, as I've done here, you can then solve for B, and you see that B is given by this quantity right here. So here's our second coefficient that we need to calculate right here. Okay, so substituting back into the equation, we see our solution here, and finally we see the solution to the differential equation right here. Now, so for part B, what we need to do is differentiate our solution, as I've done here, and then what we want to do is find out when that's 0, and to do that you must factor it, which is what I've done in the next 3 steps here. And finally we see that the solutions are given by you can find it. It's 0 when x is 0, it's 0 when x is L over 2, and it is the derivative is 0 when x equals L, given by this factor. So the maximum deflection does occur, well, in the middle at L over 2. And the reason for that is, well, I guess symmetry would be the physical reason if you imagine a beam. But the other fact is that we know that a function obtains its maximum or minimum for that matter at when the derivative is 0. So, okay, I hope this has been helpful. Thank you. I'll talk to you later.